Yo, what's up YouTube? Welcome back to Intuition. In today's video, we're going to be answering some questions on body fluids. This is a good topic for pharmacy and medical students who wants to understand how the body deals with dehydration and electrolyte imbalances. Okay, so with that said, let's hop into it. Let's dive into question number one. Okay, question number one says, a patient with cerebral edema is to be treated with a hypertonic solution. What type of hypertonic solution could be used to treat this patient? Select all that apply. Okay, so here we have a very straightforward question. It's just asking us what type of hypertonic solution could be used to treat a patient with cerebral edema. Cerebral edema is a term for brain swelling. And when you have swelling, that means that fluid, water, is built up in the interstitial spaces between the cells. And the way to drain the water out is to load the vein up with hypertonic solution to make it very concentrated so that water flows from the interstitial space back into the veins so that the kidneys can eliminate it. And of course, water is going to flow from low concentration to high concentration due to osmosis. Now, when it comes to choosing the right type of hypertonic solution, it's all going to be based on choosing a hypertonic solution with osmoles, aka particles, that are going to remain in the veins, in the extracellular fluid. And these types of particles are called effective osmoles. For example, take potassium. Within the body, sodium is primarily concentrated outside the cells. So that would be within the veins and within the extracellular fluid. Whereas potassium is primarily concentrated within cells. We know that the body does this on purpose. It pumps potassium into cells and it pumps sodium out of cells. That creates an electrical gradient that allows us to generate energy. Potassium is going to end up being non-effective as a hypertonic solution because the potassium is not going to remain in the veins. The body instead is going to pump the potassium into the cells and concentrate the cells with potassium. And therefore you end up losing that hypertonic solution in the extracellular fluid. And this example shows the general idea that non-effective osmoles are particles that the cells can take in. So you want particles that remain outside of the cells. And that's going to be the key to getting this question right. So let's go ahead and look at the question again. The first chemical is dextrose. Dextrose, clearly that's going to be non-effective osmole because that's a type of sugar, right? That is a type of nutrient that cells take up to generate energy. That would be a non-effective osmole and that will not work. Next we have saline. Saline, that's salt, sodium chloride. Just like we just said, sodium chloride primarily remains outside the cells. So this would be an effective osmole and this would be a correct answer. Then we have potassium. This is the example that we just did. Potassium will be pumped into the cells. Non-effective osmole, incorrect. Then we have mannitol. This one you should be familiar with. You should know that mannitol is one of the hypertonic solution alternative to saline that is used to treat cerebral edema. So mannitol will be a viable option. And lastly, we have glucose. Clearly, unless you have diabetes and your body is not able to take up glucose, glucose is going to enter cells and be used for energy. So glucose will be non-effective osmole, okay? So the correct answers will be saline and mannitol, all right? Cool. Okay, let's go on to question number two. Question number two states, an 80-kilogram patient with gastroenteritis suddenly develops hyponatremia with a sodium level of 130 milliequivalents per liter, down from 140, and weight loss of 3 kilograms. What are her final extracellular and intracellular fluid volumes given the following initial fluid volumes? Total body water was 48 liters, intracellular fluid volume was 32 liters, and extracellular fluid volume was 16 liters. When it comes to being able to answer questions like these, you have to be very careful. And the main thing that you have to watch out for is that whenever you change the osmoles within a certain compartment, whether you change the osmoles within the extracellular fluid or you change the amount of osmoles within the intracellular fluid, the body is always going to adjust itself through osmosis. Because even though particles are not always free to be able to move from compartment to compartment, water is, because cell membranes are concentrated with water channels called aquaporins, which allow for the free movement of water inside and outside of cells. So whenever you change the amount of particles within cells or outside of the cells, water is going to move from one compartment to the other to balance out the osmolarity within each compartment, because the body is always going to try to maintain homeostasis, aka equilibrium. So that is the main thing that you need to understand when it comes to fluid calculations. Now, the second big thing that you need to know when it comes to fluid calculations is that you can always estimate the osmolarity of the body by doubling the concentration of sodium. There are so many different types of particles inside the body that you need a shortcut to be able to estimate the osmolarity. The good news is that you can simply take a sodium level and double it, and that usually gives you a very good approximation as to what the osmolarity of the body is. Okay, so we can always know the osmolarity of the body by doubling the sodium concentration. Okay, so that's the second big thing. With those two concepts in mind, we're ready to be able to tackle this question. So within this question, this patient had gastroenteritis, which means that her GI tract is inflamed, and because her GI tract is inflamed, fluid from the veins ends up leaking out and exiting out her body as diarrhea, right? She had pretty severe diarrhea to the point where she lost 3 kilograms of weight. And of course, this weight is going to be mostly water weight. And not only did she lose water, but she also lost particles because her sodium concentration went down to 130 from 140. So she lost water and she lost particles. So water is going to adjust itself to make the osmolarity equal within the compartments. But the particles, for the most part, will remain trapped because for this patient, all the particles that were intracellular are going to remain intracellular because she didn't have any trauma, right? She didn't have any destruction of her cells. So where did she lose the particles from? She lost the particles from the extracellular fluid. We want to calculate how many particles were lost from the extracellular fluid. How do we do that? So initially, the sodium concentration was 140. If we double that, we get 280. So the initial osmolarity was 280 milliosmoles per liter. And initially, her total body water was 48 liters. So we multiply 280 milliosmoles per liter times 48 liters, and this gives us 13,440 milliosmoles. So this was the total amount of particles that this patient had in her body before the diarrhea incident. Now let's calculate how many particles remain after the incident. The sodium concentration went down to 130, and if we double 130, we get 260. So the body osmolarity ends up being 260 milliosmoles per liter. And she also lost 3 kilograms of weight, and this was water weight. And the specific gravity of water is 1 kilogram per liter. So if she lost 3 kilograms of weight, she lost 3 liters of water. So her total body water has gone down from 48 to 45. So we multiply 260 times 45, and that gives us 11,700 milliosmoles. So how many particles did she lose? We just need to take the difference between 13,440 and 11,700, and that gives us 1,740 milliosmoles. So this is the amount of particles that she lost from the body, and of course, the particles lost came from the extracellular fluid, not from the intracellular fluid, because her cells remained intact. So we know that 1,740 milliosmoles of particles were lost from the extracellular fluid, but now we need to know how many particles remain in the extracellular fluid. So let's take a look at how many particles we had to begin with in the extracellular fluid compartment. Okay, so initially the osmolarity of the body was 280, and the initial volume in the extracellular fluid was 16 liters. So we multiply 280 times 16, and that gives us 4,480 milliosmoles. So now we take the difference between 4,480 and 1,740, and this difference comes out to 2,740 milliosmoles. So that is the amount of particles that remain within the extracellular fluid after the incident. So now we know the amount of particles remaining in the extracellular fluid, and we also know the final osmolarity of the body. So we just need to divide 2,740 milliosmoles divided by 260 milliosmoles per liter. And when we do that, we get 10.5 liters. Initially, we had a volume of 16 liters in the extracellular fluid, and that has gone down to 10.5 liters. And now to get the final intracellular fluid volume, we just need to subtract 10.5 from 45 because the total body water after the incident was 45 liters. So we have 45 liters, take away 10.5 liters, and we're left with 34.5 liters. So that is the volume of the intracellular fluid. So we have 10.5 liters and 34.5 liters. Easy, all right? Cool. Now let's go on to question number 3. Okay, question number 3 says, the previous patient refuses fluids because she does not feel thirsty. She simply wants to correct her sodium level by consuming table salt. Sodium chloride has a molecular weight of 58.5. How much table salt would the patient need to consume to correct her sodium level? Okay, so the patient is refusing fluid, which is definitely a bad idea, right? She's clearly dehydrated. She needs fluids and electrolytes to get her body back into good shape. So this is definitely not a good idea on her part, but let's go ahead and answer the question to see how much sodium she would need to consume to get her sodium concentration back to normal. Before she eats all the salt, the amount of particles that she has in the ECF was 2,740 milliosmoles. The amount of particles that she has in the intracellular fluid never changed from the beginning because no particles ever left the intracellular fluid. The cells always remain intact. So the initial amount of particles we had in the intracellular fluid was 280, which was the initial osmolarity of the body. And the initial volume of the intracellular fluid was 32 liters. So 280 times 32 is 8,960 milliosmoles. So these are the amount of particles that she has before she consumes the salt. And we're trying to figure out how much salt she should consume to get her sodium level back up to normal. So we're going to say that she's going to consume X milliosmoles of sodium. And this sodium is going to remain within the extracellular fluid. So this is going to add to the milliosmoles of the extracellular fluid. So we're going to have 2,740 plus X milliosmoles after she eats the salt. And of course, the amount of particles within the intracellular fluid will remain the same. That's not going to change. So that's going to remain 8,960. Now that she's trying to get her body osmolarity back to normal, for the extracellular fluid volume, that's going to be 45 liters, which is the total body volume of water, minus the amount of water in the intracellular fluid. And now here's where we get clever. We can figure out what the volume of the intracellular fluid is because she's getting her osmolarity back to normal, which means that she's getting her body osmolarity back to 280 milliosmoles per liter, which was the initial condition. Now remember, for the intracellular fluid, the amount of particles within that compartment never changed. The amount of particles within the intracellular fluid remains the same, and if she's going to get her body osmolarity back to normal, then that means the fluid volume within the intracellular fluid is going to go back to what it previously was to begin with. And initially, the fluid volume of the intracellular fluid was 32 liters. So if she consumes the right amount of salt to get her osmolarity back to normal, her intracellular fluid volume will be 32 liters. And now that we know this, we can figure out the extracellular fluid volume, which will be 45 minus 32, which will be equal to 13 liters. So 13 liters will be the fluid volume for the extracellular fluid, and 32 liters will be the fluid volume for the intracellular fluid. All right, so now we're ready to solve for X. Her body osmolarity will go back to normal, so it's going to go back to 280 milliosmoles per liter, and that's going to be equal to the amount of particles in the extracellular fluid, which is 2740 plus X, divided by the volume of the extracellular fluid, which is 13 liters. And now we just need to solve for X. So X is going to be equal to 280 times 13 minus 2,740. So that gives us 900 milliosmoles. So she's going to have to consume 900 milliosmoles of sodium chloride. And we know that 140 milliequivalents of sodium is equivalent to 280 milliosmoles of particles. So we just need to multiply 900 times 140 and divide by 280. So that ends up being 900 divided by 2. So that ends up being 450 milliequivalents of sodium chloride. Sodium chloride has a valence of 1, and therefore a milliequivalent of sodium chloride is equal to a millimole of sodium chloride. So 450 milliequivalents of sodium chloride is equivalent to 450 millimoles of sodium chloride. Okay, and 450 millimoles of sodium chloride is the same thing as 0.45 moles of sodium chloride. And we know that the molecular weight of sodium chloride is given as 58.5 grams per mole. So we multiply 0.45 times 58.5, and that gives us 26.3 grams of sodium chloride. She will have to consume 26 grams of sodium chloride to correct her sodium level, which is a lot of sodium. So that's definitely not something that she'll want to consume all at once. An IV drip will allow her to be given this amount of sodium over an extended period of time so that she's not given a large amount of sodium at once, which can cause a seizure, right? You don't want to do that. So it would be best for her to take the fluids and not consume this much sodium. All right, so I hope that was helpful. If you guys have any questions, leave it in the comment section below. Go ahead, subscribe to the channel if you haven't already. Go ahead and like the video, help the channel grow. Leave a comment for the YouTube algorithm, help the channel grow, and subscribe. And go ahead and share the video with people who you think would benefit from the content that we provide on this channel and help us make the world a better place. Keep watching, keep learning, and as always, I'll see you guys next week. All right, bye-bye.